In this session, I'll be treating the topic of multivariate statistics. Here are some references. I will show a simple case. I just found this paper online. It's a nice paper in the sense that it has some application of both co-kriging and co-simulation. For other reads, I refer to the book of Pierre Gouvert's and also the book by Hans Wackernagel, who has written a really nice book on multivariate geostatistics in particular. Okay, so what's the case study that we'll cover here? It's a case study where we try to estimate soil loss. And so again, what we have is a number of sample locations where we have estimated soil loss and potentially also other variables. And we have some covariate information, such as a digital elevation model, the slope, etc., reflectance, etc. So the question therefore is, can we create a map of soil loss given all this information and potentially quantify uncertainty? Okay, so that's the aim. Soil erosion is a function of many variables. I'm going to go into details of all these different variables. But this reminds you perhaps of the spatial aggregation, data aggregation session that we covered, where we looked at several variables and how they would inform a target variable, in this case, soil erosion. So you may question now, well, why can't we just use spatial data aggregation? Well, remember in spatial data aggregation, we were looking particularly at modeling something that is present or absent. For example, mineralization is present or absent. Geothermal system is present or absent. So now we deal with a continuous variable. Now we also have ground observations, and we'd like to create maps, not just train on those ground observations, but on these, we want to also fit the ground observations, just like we did in kriging and simulation before in sequential Gaussian simulation. What also is not done in spatial data aggregation is that there's spatial correlation between all these variables. We just kind of looked at what I would call the co-located information. So we looked at pixel-wise comparison and compared only pixels that were at the same location. We didn't look at the spatial correlation that may exist between pixels at different locations. So, and then we also, of course, we need to quantify spatial uncertainty and its impact. So to do that, we'll again use geostatistics, and to quantify spatial correlation, we'll look again at the variogram. And so here we see the variogram of the various factors, but then also what we'll be looking at is what's called the cross-variogram. So now we have taken our variogram equation, which previously looked like, say, this here with a square. We now say we remove the square and we put this other term in here, but this other term has to do with another variable. So we're looking here, for example, at the cross-variogram between LS factor and C factor. And we notice that this cross-variogram can be negative. This indicates some kind of a negative correlation that may exist. And so we also need to model that particular variogram. So if we do that properly, and we can do that for all variables, then now we can do co-kriging. For example, we do co-kriging of the soil loss. Here is if you just use spatial data aggregation, the methods that we've seen before, such as weights of evidence, then we get this map. Doesn't look very informative. Well, if you do co-kriging or co-simulation to characterize spatial uncertainty, we get maps that have much more granularity, and so they're much more interesting in terms of, say, studying the impact of soil loss on other things. So that's the idea. So the idea is essentially to take the kriging that we've developed before and the simulation methods that we developed before, which were only dealing with one variable, and extend them to now including many variables at the same time. So here's just another illustration of the same idea. So the two variables we're considering now are in the subsurface, and they are called porosity and permeability. And of course, we know porosity and permeability tend to be correlated. Permeability tend to be larger when porosity is larger. That's not always the case. So the question then we have, say, for example, if we have measured porosity and permeability at several locations, and here we'll just look at standardized variables, how would you now jointly model these two variables in space? In other words, what's in between the data points? So one thing we can do, as we've done before, is just do kriging of the porosity and kriging of the permeability, or we can do SGSim of the porosity and SGSim of the permeability. So, however, if we know there's correlation between those two, and suppose the pointwise correlation here is 0.8, And we know that these independent simulations are not really capturing what happens in reality, namely that they are correlated. So here we have an example of Co-SGSim, which is a method we cover later. So here's another simulation, etc. So I can simulate many. And then I ask myself, for example, a question. If I've done that and I've ignored the spatial correlation, what is the probability that my porosity and permeability, say, is above this red line? So if you look at that, for the marginals, that's not very different between this case, the separate simulation, and this case, the joint simulation. But if you look at the joint exceedance over threshold, then we see in the separate simulation, I get much less than in the joint. And that makes, of course, sense if they are correlated. And if one goes above the threshold, then it's more likely the other goes above the threshold as well. And so that is something that we'll need to take into account because this may affect results, such as, for example, when we would do flow simulation on porosity and permeability models. It's better that then, of course, they reflect reality, which is that they are correlated in space. So let's again revisit the equivalences and differences with univariate versus spatial. This is something we'd also when we look at Gaussian simulation or stochastic simulation in one variable. So in a univariate case, we have a single random variable, and we have a probability distribution that models the uncertainty on that particular variable. In the multivariate case, we'll have now, in that case, we would have multiple random variables. And so at a minimum, we'd have to specify the multiple probability distributions and also some correlation coefficients. For example, if I assume the multivariate Gaussian applies to this case, then all these univariate distributions are Gaussian, and these correlation coefficient model the linear correlation that exists between these variables. So when we now go to the spatial case, remember, we take our single random variable, and now we have a single random function and a single variogram. So when you go now to the multivariate case, we now have multiple random functions. So each random function models a different variable. For example, that these could be the 6 variables that we are modeling in the soil loss case. As a consequence, now we also have multiple variograms for each variable. And at a minimum, we need to also look at multiple cross-variograms. That means what's the cross-variogram between 1 and 2, 2 and 3. So that's something that's related to the or is the equivalent, say, of these correlation coefficients. So let's talk a little bit about these cross-variograms. What are they? So as an example, and I'll revisit the example extensively later on, is where you say you have two variables. Let's call the variable u and the variable v, and we see that they're different in nature. The v is a little smoother than u, and we may have sample locations where we have both u and v. And so what we're now doing is we have, of course, the variogram of u, the variogram of v, and potential. And if I have only sample locations, I would do that based on the sample locations. So that would be what was called the primary variogram. Now, this primary secondary is a little bit perhaps confusing. We don't have to choose what is 1 and 2. We can call this 1, we call this 2, this 2, this 1. So typically, Z1 is called primary, and Z2 is called secondary. And that has some reason later on when we talk about collocated co-kriging and specific examples that involve only 2 variables at a time. Let's say the variogram of the first random function, the variogram of the second random function. And then what we can do is we can simply take a variogram, a cross-variogram that is has to do with the correlation between something that's over here and something that's over there. So we're switching around now. Essentially, we need to look at the correlation between something that's primary over here and secondary over there. So we're extending this notion of that. So on a theoretical note, perhaps, is that we have the classical variogram estimator, and that's the one we've seen before. It's the average square difference between any 2 points at a certain lag distance h away. And so the extension to that for a cross-variogram is the equation below. So we just, as I said, remove the square and add the second term to it. And that is then our cross-variogram estimator. Now, in the literature, we also see another estimator, which is called the pseudo cross-variogram estimator. It's not really a variogram, but it can be used also to derive your own co-kriging equations. The reason why this is more sort of appealing than this one is that for this one, we can have data that don't have to be at the same location. You can see here, in order for me to calculate that, I have to have data of Z1 at location x alpha and z2 at location x alpha, and also z1 at location x alpha plus h and z2 at location x alpha plus h. So in this equation, I don't have to have that. I don't have to have these data that are at the exact same location. So this applies much more to sort of the general case. And you can use this one to develop your own Co-kriging equations. But that's just a theoretical note. But keep that in mind if you have cases, say, where it's very difficult to estimate the traditional cross-variogram. So here we see now the various variograms for that case that I showed before, the worker lake U, the worker lake V, and then also the experimental cross-variogram. And so because we have a positive correlation between the two, our cross-variogram looks somewhat similar in shape as the experimental variogram. The only thing you will notice the difference is that, for example, the V experimental variant was a smooth image, so we have less variance, so the still a smaller and smaller nugget effect, while for pointer on here, so we have less nugget effect and less variance than, for example, the primary variogram, which has a higher variance and a higher nugget effect. And so logically, we find that the experimental cross variogram is somewhere in between. So it does signify that there is spatial correlation between. What does that really mean? There is spatial correlation between a primary and a secondary variable at a distance 20. But if you go further and further, then that correlation will start to drop down and become 0. Okay, so a typical situation you face is that, as I said, the primary and the secondary phase and the secondary example is that you're needed to estimate or simulate a target or primary variable of interest. For example, it could be permeability or porosity would be perhaps a better example. And you have some what's called point data at a few locations where you have measured porosity. But then also you have some exhaustive secondary variable that is indirectly related to the primary variable. And that could be, for example, geophysics. So say a seismic impedance, which is typically related to porosity, and due to its coverage, is measured everywhere. And so that's a very typical situation when you're dealing with two variables. And this is a situation we'll discuss in more detail. So in your homework that you'll be looking at, that's the kind of case that we have. Here we're in a groundwater situation where we measure porosity along boreholes, and we have SkyTEM EM data that is exhaustive. And you also notice that the SkyTEM data has smaller variation than the porosity data, which is higher variation. So we'll call this the primary target variable, and this is the secondary exhaustive variable. Okay, so this is kind of the situation that we have, is we have some exhaustive secondary or soft data, and we have some primary hard data. And so previously we only looked at primary hard data, and we said our kriging estimator is written as a linear combination of these 4 data points, and that was this first part here. And the way we derived those equations was say, okay, I need to account for correlation between the unknown and the data, and also between redundancy between the data. These two should share their weight. And so the kriging equations were designed to account for all that and solve for these particular weights. So now it's actually very simple. Now we just extend the same idea, but we're adding more terms to it. So again, we have a linear combination of the secondary data. So you don't have to worry about the units here. The units will be taken into account by the weight. So that doesn't really come into play here. So we have, as you notice, those everywhere. So we have many more of this than this. Okay, so that's the kind of problem that we often deal with. Now, the co-kriging and co-simulation methods, they can be extended to any kind of situation we're dealing with. You can have less of these. These don't have to be at the same location. And so that can, but the methods essentially remain exactly the same. So what were kriging equations, and how do we solve for those weights? Well, as I reminded you in the previous slide, is that we need to look at 2 types of covariances. So covariance between the data, and so if you have n data, you have an n by n covariance matrix, and the covariance between the data and the unknown. And so that's your n times 1 on the right-hand side. So now, because we have more data, all of this data will go again into covariance between data here and covariance between data and unknown here. And so what we have now is to solve this system, what we need is now the covariances between the primary and the unknown. That was our primary covariance. This is our classical kriging. But we also have the covariance now between the secondary and the unknown. So the secondary information provides information on this unknown, and so that's now a cross covariance, and so on. So I also need to account for, in the blue term here, the matrix, I have primary, secondary again, and also have redundancy in the secondary information, which is measured by the secondary covariance. So now the system of equations is no longer n times n, but is, if I have here n1 data and n2 data, the system here is n1 plus n2 times n1 plus n2. And this right-hand side has n1 plus n2 size of the vector. So that is called the full co-kriging. And the full co-kriging is difficult to do in reality. It sounds nice on paper, because we run into the same problems as we ran into when we dealt with variogram modeling for just one variable. And we saw in variogram modeling with one variable that we have to have a positive estimation variance, and that restricted us to essentially using only particular functions. So now we are in an even more difficult situation. Now we have functions, variogram functions for each variable and a cross-variogram function. And so now we have to worry about the positive definiteness of all these functions together jointly. And so that's a difficult thing. So we want the variance of all these linear combinations to be always positive. And so that means that that for all weights here, that this quadruple sum over all covariances between any n cross covariances have to be positive definite. And so that becomes a very bit difficult situation to handle. It's not an impossible situation. There are methods for doing full co-kriging, and they work relatively well when you have very few variables. But then on the other hand, we can also imagine a situation like this one, where the secondary data is perhaps relatively smooth or relative to the primary data. That would be true in that case, say, of the porosity and the SkyTime data. So that means that the information that really only matters for estimating the primary variable at this location is not to use all of this secondary data, but only use the co-located one. So it doesn't mean that that essentially all this other information is independent of this one, but we have now we're imposing a condition, an assumption here of conditional independence. So we say that if I know this guy here, that's enough for me to know this guy. I don't need to know all the other guys over there. So I still, of course, keep the primary data. So that's going to simplify things tremendously, as we'll see with the theory in a little bit. And so this method is called co-located co-kriging. So now we say that we have n primary data and only one secondary data that we use. And so in that case, we need to define only one weight. So that leads us to simplified covariances model, cross-covariance modeling. And this paper by Janelle in 1999 illustrates nicely two methods for doing such covariance modeling, namely the Markov models. And we'll be discussing those in a little bit of detail. Okay, in that paper, we treat really two situations. So the first situation is somewhat perhaps the classical subsurface situation, where you drill and you measure things and you find things highly varying. And so you have your primary variable that's highly varying. And then you take geophysics and you find that it's much slowly varying because it filters out a lot of the detail. And so our primary variable is much more smoother. And the unknown truth, of course, is highly varying. So that is situation one. That's not the only situation. We may actually have the reverse situation. We may have the situation where our primary data is very slowly varying and our unknown primary truth is very slowly varying, but the information we get on it is very highly varying. So the Z2 variable is now highly varying. So I kind of switched the whole situation around. So one is really the subsurface case, as I mentioned, for example, seismic data and porosity. So where seismic we'll call secondary or soft data, and the primary or hard is then the porosity. In remote sensing, however, it's the opposite. Our remote sensing image needs to be processed. And so our target is a remote sensing image, which is then slowly varying. And we may have some ground truthing observations that are highly varying. Somebody goes on the ground and makes observations. And so then we have a much more highly varying truth data. And so that means our primary data is slowly varying and our secondary data is highly varying. So we have to keep those in mind because they will lead to different modeling assumptions. Okay, let's now work gradually towards a mathematical expression of what this all means. So here we say the situation one is that secondary data is smoothly varying, but it's measured at a larger scale, for example, and primary data is measured at a much smaller scale. So here this is the situation is explained here in the same way. So we have the red data, which is it has constant values, say in the squares, and then the blue data or the blue variable is varying in those individual squares. So what we're saying is, if I am in this particular point here, so if I want to estimate some blue over here, I don't need to use this red data. I only need to use the collocated data over there. Okay, so what does that mean? So this is called the Markov Model 2. And so you'll think, yeah, what about the Markov Model 1? Well, that comes later. That's the situation 2. So in this situation, we're saying, as expressed before, that the conditional expectation of a primary variable at location u given two secondary variables at other locations is conditionally independent, so that returns simply to the collocated one. The mathematical result, which I'll show briefly in the next slide, means of this assumption essentially means that that our cross-variogram h is our correlation coefficient times our secondary variogram. So here I write everything with correlograms instead of variograms. The reason for that is that I'm going to standardize everything to mean 0 and variance 1, which makes the derivation simple. So you can just think here variogram, but then unstandardized. So no mean and 1. I mean, it's not 0 and variance doesn't have to be 1, but this is just for illustration. Okay, so that's good. I have now my cross-variogram. What I also need, of course, the primary variogram. The secondary variogram I don't need in the Kriging equations because I only have one secondary data, so I don't have to worry about secondary data that are correlating with each other because I only have one. So our primary variogram will be written as a function of the secondary variogram times the correlation coefficient plus a second term which is a residual term. And this residual term we see in a bit is needed because the secondary variogram, of course, is slowly varying. And so we need a high varying component to essentially add up to that. So the idea in Markov Model 2, which I'll come back to, is to model the secondary variogram first, calculate the, then from that you can calculate the cross-variogram with the correlation coefficient, and then model the primary variogram in a separate way. Okay, so how did we get to this particular equation? So let me give you just the derivation, just FYI. It's of course not important if you go to the practice and do actual modeling. So what we want to have, or the assumption that we are imposing is this conditional independence assumption on the expectation. The second assumption, of course, that we make in all of linear regressions is that the primary and secondary variable are linearly related. And so because we're dealing here with standardized variables, mean 0, variance 1, this is simply written as function of the correlation coefficient. So what we're interested in is what if I make this assumption here, what is now the cross-variogram? Well, the cross-variogram is defined as such, again, under 0 mean and variance 1. So this is an expectation, so I can write this expectation conditionally to two things, and I would like to put that in now because I'd like to get to this particular condition, times this bivariate distribution for a particular lag distance. So now we see here that per 1, of course, that this here is no longer important, so that drops out, and of course now this becomes independent. This is no longer dependent on this right-hand part, so I can drop that out as well, and that becomes this value z2 prime. So what I'm left with is this guy given that guy and the bivariate distribution. Okay, so now this is my linear regression. So this is my linear regression. So I write that like that. And I put this linear regression out the front, and I have this here. And this is simply nothing more than the correlogram of the secondary observation. Okay, so that is what we had in the previous slide. What about the primary? Well, in the primary, the way it's going to work is simply saying that, well, my primary is essentially, I can write it always as my secondary times correlation coefficient plus something I'm missing, a part that's missing, because remember the primary is much more highly varying, and so I'm going to write this in this fashion. And so then by assuming that R of u independent of z of 2, so is an independent component, then we find that the correlogram is simply equal to this here. Just note that there should be no square over here. Okay, let's do an example. So here I have a case where I have the Z1 data, which is highly varying point data, and then much less varying Z2 data, which indicates some kind of a trend, or could indicate some kind of an average of these properties. The problem often with these kind of situations in reality, and certainly in the subsurface, which would be an equivalent here, is that you don't have enough Z1 data. And so in that case, what often people do is they look at analogs. They look at some other data set where they have exhaustive information and they can start modeling variograms and cross-covariance. So once you have that, so and that's what we have here on the right-hand side, we give ourselves some nice exhaustive data. We learn all the essentially the cross-variogram, variogram, secondary variogram, primary variogram from this, and then we use that model to do our co-kriging and co-simulation on the right-hand side using this data. So imagine now you want to do simulation. So we're going to extend the notion of sequential Gaussian simulation to co-simulation. So what that means is that instead of using just the primary hard data, I'll also using the secondary exhaustive information in my simulation. That's called co-SGSim. So co-SGSim is exactly like SGSim, except now that you're doing kriging, co-kriging instead of kriging. But all the other operations are the same. So what we need to do is, first of all, is to perform normal score transformations. So what we do here is we do a normal score transformation on the hard variable, that's our analog, and our soft variable analog. And we can now look at the correlation coefficient, which we notice here is 0.76. So the next step is that's going to happen in Markov Model 2. Let me put my pointer on. So here's that correlation coefficient. So the next step we have to do is to calculate and model the secondary variogram, namely the variogram of Z2, then calculate the correlation coefficient between Z1 and Z2, and then calculate model the primary variogram using this particular equation. And I already have, of course, the secondary variogram. That's what I had before here. Okay, let's go through these steps. So we did the normal score transform. So the first thing we have to do is calculate and model the variogram of the secondary data. So here, that's that. So we have our secondary data, and we have our variogram. So you notice, of course, it's smooth, it's Gaussian. Notice that the cell is 1, and so I can use the SGM tools to do a model. And here you see that I have a model in here with a range, and isotropy, etc. Notice that the contribution here is 1. I notice also I have no nugget effect. So this is an easy variogram model to do, of course. So we have that simple variogram model. So now I need to calculate, I can calculate the cross-variogram simply by multiplying the correlation coefficient with correlation coefficient with secondary variogram. So now what I still need is the primary variogram model. The primary variogram model, the way I'm going to do this is to have two structures. I have a structure that I already know. This is my previous guy here, so that's over here. So now you see in my model that I have for this information, I have two structures. Structure is component 1. Remember what the structure was, right? And the structure was essentially that you had variogram is contribution 1 times variogram 1 plus contribution 2 times variogram 2. So that I can do that in SGMs by having two structures. The second structure I have to fiddle around with because this is now fixed. And so the only thing I would know is the contribution. Because that's the square correlation coefficient. Square of 0.76 is 0.57. And so what I have left is 0.33 if I count also for a nugget effect. And so here what I find is that my second variogram component is isotropic with a range of 32 and is exponential. Remember that this one was Gaussian. So now I have everything. I have a primary variogram. I have a cross-variogram. That means I can do co-located co-kriging. If I do co-located co-kriging, then I can also do co-simulation or co-SGSim. And that is shown here. So this is our case from the previous lectures where we had hard data and we did model the variogram and the histogram, and we came up with a sequential Gaussian simulation. So now I have both hard data as well as soft data, and using the co-kriging, I now simulate this phenomenon with both information. And of course, we notice that there is a considerable improvement in terms of, say, compared to the actual Walker Lake data set. We see, of course, because this secondary data tells us where the mountain is and the lake, it's hard to tell that from just the primary data, that our co-simulation is now reflecting really nicely the kind of structure that we actually have in reality. Okay, so now we turn ourselves to situation 2. So recall that situation 2, our primary variable is slowly varying, our secondary variable is highly varying. And so the Markov model now is very different. It's basically reverse. It means essentially, like here, it means that if I want to model the blue big square, then I can essentially ignore whatever is in this square. I can only use the information that is in that square, so that I only use the secondary data in the same square at most. So previously, this was our Markov model 2. So our Markov model 1, we just diverse Z2 and Z1, and we get this other condition here. So that means essentially this condition. This Markov model 1 leads to easier equations. First of all, what it leads to is that the covariance of the secondary variable is simply the primary variable times the correlation. The cross covariance is simply the primary covariance times the correlation coefficient. And again, because we don't need the secondary variogram in collocated co-kriging, we're basically done now. So in practice, you model just the primary variogram, and then you multiply the primary variogram with the correlation coefficient. So what that means in SGEMS is that the only thing you're going to input is the primary variogram and the correlation coefficient. There's no need for inputting anything else. So it's the same situation. We were doing normal score transform, calculate and model the variogram, and then calculate the coefficients of correlation. Okay, so here is our primary variable. Remember, our primary variable is smooth, so we have that same smooth variogram as we've seen before. And we calculate the correlation coefficient, which is 0.76, and we can now do essentially conditional simulation. So here is our secondary data. Remember, our secondary data was highly varying. This is unconditional Gaussian simulation, and you see that it's smooth, right? Because our primary variable is smooth, but it's not controlled by this mountains here. So when I go to do co-simulation, then I see, of course, that I see this mountain appearing here, and so and the valley as well, and so I get much more accuracy in terms of my predictions. So for those who are working in subsurface, a little bit of a warning. What we often see is that people like to use Markov Model 1 simply because it's very easy. You just have your variogram modeling you do traditionally, which is the variogram of your primary data, and then you calculate the correlation coefficient. And often in the subsurface, this is done by looking at well locations, such as here, for example. And at those well locations, you have both the primary and the secondary data. For example, this is an impedance cube. This is seismic data. These are drillings that have porosity. And so you put on my pointer. So the porosity drillings, impedance cube. And so what you get is, in this case, you have actually two faces, but it sort of doesn't really matter that much for what I'm trying to show, is that you get a certain correlation coefficient, which is minus 0.67. So now you say, well, I'd like to do Markov Model 1, but in reality, of course, Markov Model 2 applies. So what's going to happen if you use Markov Model 1 is you're going to model the primary variogram. You have a correlation coefficient, and you're going to go ahead and do simulation. So simulation, as you remember, we'd like to reproduce the histogram of our data, the variogram of our model, and also the correlation coefficient between the simulated realization and the secondary data. So in addition to doing the regular checking of where the histogram and variogram are reproduced, you'd like also, of course, have your correlation coefficient reproduced, because that's the one you have observed in your actual observations. So let's do that. Let's generate a model of porosity. And so this is what we get. Looks nice. But when we look at the correlation coefficient, we find now that it's much higher than 0.6. And so there's too much correlation. So you have to think a little bit about why that is. And to answer that question, I suggest you look at what are the exact assumptions being made in these Markov models. What is the assumptions being made in the Markov Model 2, in the Markov Model 1, and what would happen if I would apply that to a situation where really the Markov Model 2 applies? If I do the Markov model too, therefore, you notice that I get much less correlations, much less sort of following the secondary data. And so now if I calculate the correlation, I find that's pretty close to 0.6. So we get minus 0.57. So do be careful in not using the method that's easiest to use and use the appropriate method. Because otherwise you run into problems of creating uncertainty that's essentially too small in this particular case.